Hello everyone, welcome to this new session on switching theory and logic design. We are discussing Boolean algebra. In previous session we have discussed one important theorem, De Morgan's theorem. In that first law we have seen it states that a plus b bar is equal to a plus b bar equal to a bar b bar. So this is very important law what we have studied. So today we will see De Morgan's second law. So De Morgan's second law is also very important and very easy and as well as interesting. So let us begin with today's session where we will see second De Morgan's law. Say second theorem or law 2. Law 2 for De Morgan's. Okay, so second law states that AB bar is equal to A bar plus B bar. Now this law states that complement of the product of variable is equal to the sum of their individual complement. That means the complement of two or more variables ANDed together is equal to the sum of the complement of each individual variable. Now from schematic we can see what is LHS. For LHS, if we draw LHS, so we have AB, that is AND operation. A and B are the inputs for say AND, and after that their product is connected to inverter, so the total output is A B bar. Now if we remember the circuit of NAND gate, NAND is nothing but AND plus NOT gate. So this is equivalent to NAND operation. So we can say this is nothing but equal to NAND. This is LHS. Now RHS we can draw similarly. For RHS we can draw as, what is statement of RHS? RHS is sum of, I will write down here, say RHS statement is say A bar plus B bar. So first we have to take A and B inputs, say A and B are the inputs, so its complement we have to take, so we will connect one NOT gate. So here we'll get A bar, here we'll get B bar. Now we have to take sum of these two. So for taking sum we use OR gate. So its output is A bar plus B bar. But now this one, if you observe keenly, this is like bubbled OR gate. At the input we have inversion and then we are taking OR operation, OR for NOT followed by OR. So this is nothing but bubbled OR gate. So on OR gate we can show two bubbles representing the inverter. So this is A B input, and at output we get A bar plus B bar. Now let us compare the truth table of LHS and RHS. First, let us note down the truth table for LHS. We have A, B, two inputs, and output is AB bar. Possible inputs are 0, 0, 0, 1, 1, 0, 1, 1. So if we take AB bar, here we will get 0, 0, AB is 0, but its complement will be 1. Here we will get 0, here also we will get 1, 1, 0. This is the output for LHS. Now let us check output for RHS. Say we have inputs as A bar, B bar, and output is say A bar plus B bar. So for AB 0, 0, A bar, B bar will be 1, 1. For AB 0, 1, it will be 1, 0. For 1, 0, it will be 0, 1. For 1, 1, it will be 0, 0. Then addition of this 2, 1. Addition of these 2, 1. Addition of these 2, 1. Addition of these 2, 0. So here we can see the output of AB bar is 1, 1, 1, 0, and A bar plus B bar is also same, that is 1, 1, 1, 0. Now this is like LHS is equal to RHS. So now this law can be used for multiple variables also. For example, if we extend the number of variables, say we have A, B, C, D and so on, and if we take its complement, it will be equal to individual complements addition, A bar plus B bar plus C bar plus D bar and so on. Okay, so like this we can extend it. So this now we can see that law 1 and law 2 also permit removal of individual variables from under a not sign, and we have to transform from a product of sums to sum of product form. Say product of sum form to sum of product form. Its applications we will see in the examples. Okay, so let us now see the next theorem. Next theorem is Shannon's expansion theorem. Next theorem is Shannon's expansion theorem. Now this theorem states that any switching expression can be decomposed with respect to a variable A into two parts, one containing say capital A and the other containing A bar. This concept is useful in decomposing complex machines into an interconnection of smaller component. Let us see example of de-Morganization. Say we will take one example. Example, question is de-Morganize function f is equal to a plus b bar into c plus d bar whole bar. Okay, now let us check the solution. Now what we have to do, we have to de-Morganize. So we'll see how to do that. Let us take the complement of the whole function. if you take complement of whole function, then it will be equal to, the bar will be removed, a plus b bar and c plus d bar. Now we will change AND to ORs and ORs to ANDs. Okay, wherever there is OR, we will change it to, let us change ANDs to ORs and vice versa. So here we have OR, so we will make it AND. Here we have AND, so let us make it OR. Here we have OR, so let us make it AND. And again we will take the complement of these variables. We have taken complemented, again we will take complement. So what we will get, a bar dot b plus c bar dot d. So this is the De Morganize of this function. So what we have done, we have converted the sums into products and products into sums. This is very important concept. Now let us see next example. Next example. Apply De Morgan's theorem to the expression f of AB bar into CD into, say, CD plus E bar F into AB bar plus CD bar. Now let us solve this one. So let us write it down. So this one we can, let us take the complement of this one. So if we take complement of this, we will get AB, complement of this CD bar, complement of this, say we can write, it can also be written as E bar F whole bar. Like this also we can write complement, or here we can write AB double bar, that is nothing but AB, or we can also write CD double bar. Now let us simplify this term. So here we can write AB plus C plus D bar and E plus F bar plus A, B, C, D. So this is the solution for De Morgan's theorem for this example. Let's see the next example. Reduce the expression f is equal to AB bar plus A bar plus AB whole bar. Now we can break up the upper line between AB bar and A bar, and between A bar and AB, and change the sign between, we'll change the sign between, say, AB bar, A bar and AB. So how can we simplify it? So f will be equal to ab double bar into a double bar into ab bar, right? So here a double bar, say here we'll get ab double bar ab into say ab bar, this will become say 1 0, so the whole term will become 0. This is one method. Another method also there to solve this, say we'll write down the function say we have f is equal to a double bar into b double bar into ab bar, so we can write it as say ab into ab bar equal to 0. So these are some theorems related to that. Now let us see few additional theorem. There are 2 additional theorems also. Let us see them. Say additional theorems. So in that, let us see theorem 1. Theorem 1 states that x into function f of x comma x bar comma y, say so on, maybe up to z, is equal to x into f function of 1 comma 0 comma y comma up to some z. Now this theorem states that a function containing expressions or terms with x and x bar is multiplied by x, then all the x's and x bars in the function can be replaced by ones and zeros respectively. This is permissible because say x dot x is equal to say x, so that is equal to nothing but x into 1, and x dot x bar is equal to 0, that is equal to x into 0. That means suppose we'll keep some values here in terms of 0s and 1s. Say for example x is 0, hence x bar will be 1. So let us keep here 0 into 0, it will be 0, that is x, that is nothing but x into 1. Similarly, if we take dot product of x0 and x bar 1, it will be equal to 0, it will be equal to x into 0. So whatever is here x, in that if we multiply 1, if x is 0 multiplied by 1, it will become 0. If x is 1 multiplied by 1, it will be x only. So this will not make any change. So here we can replace these terms with zeros and ones. Okay. Next theorem states that, theorem 2, says that say x plus function of x comma x bar comma y, say up to some z function, is equal to x plus f function of 0 comma 1 comma y comma some z. So this theorem states that if a function containing expressions or terms in terms of x and x bar and is added with x, then all the x's and x bars in the function can be replaced by zeros and ones. In this we will replace by zeros and ones. Previously we can replace by ones and zeros. Why we can do that? Say because x plus x is equal to x, or we can say x plus 0. Adding 0 with any number will give same number. Say x plus x bar will be equal to 1, that is nothing but x plus 1. So because this rule is valid, so we can write this theorem like this. So these are few theorems, and with this we will stop this session here. In next class we will see the different rules. We will study the duality and we will see the reducing Boolean expressions. Till then, have a good day. Thank you.